All right, here we have one more example. An archer releases an arrow 5 feet off the ground at an angle of 25 degrees with the horizontal. The initial speed of the arrow was 120 feet per second. And again, our first job is to write a set of parametric equations to model the motion of the arrow. So for part A, again, I have the generic form down here. We just fill in our information. So x is supposed to equal, this is our initial speed, which it says was 120 feet per second. So x is going to equal 120 times the cosine of the angle. It says it was above the ground and it was launched at an angle of 25 degrees times t. For my y, that's going to equal h. Now h is the height above the ground it was launched at. It was launched 5 feet above the ground, so my initial height was 5. Plus, and here is my initial speed again, was 120. This time it's the sine of our angle of 25 degrees times t, and then minus 16t squared. Okay, so those are my equations. Now again, for my calculator I need my angle in radians, so I need to change this 25 degrees to radians. So again, to do that you multiply by pi over 180. You can reduce this if you want or not. 5 goes into both of these, so 5 goes into 25 5 times, goes into 180 36 times. You really could go ahead and write your radian measure as 25 pi over 180 if you wanted, but I'm going to go ahead and reduce it. It's 5 pi over 36. So in radian measure, my equation is x equals 120 cosine of 5 pi over 36 t, and y is 5 plus 120 sine of 5 pi over 36 t minus 16 t squared. Okay, you can write either of those for your answer. I do need these for my calculator. So now I'm going to go to my calculator here. Okay, so again, I'm going to go ahead and make sure it's in parametric, and then I'm going to clear these out so I can type in my equation. Okay, which was, be very careful typing this in, 120 cosine of 5 pi over 36. I need 2 parentheses there and a t. My sine was 5 plus, because this one started off the ground, remember, 120 sine of 5 pi over 36, parenthesis, t minus 16t squared. All right, there's my 2 equations, and now all I have to do is plot the graph and then probably adjust my window. Because notice, of course, we started at 5 feet. We need to see everything up there. So I'm going to adjust the window. My minimum, I'm going to put at 5. Here, I'm going to put this, just in case, I'm going to put it at 200. See how that works. Minimum of -5 for y, a maximum of, we'll start at 50, see if that's far enough. And for t, I want to start at 0 time to 10 seconds, and if that's not long enough, we'll fix it. All right, so see now my graph's cut off. I can see the peak, so I know my y values are high enough, but my x values don't go far enough. So I'm going to double this, go to 400, see what that does. Okay, so I can see my graph comes down around 350. I probably wouldn't want to make it much smaller than that, unless you went to maybe 375 might work. Okay, all right, so there's our graph. Again, we need to find the maximum height. We need to know how far it traveled before it hit the ground, and then we'll use that to find out how much time it was in the air. All right, so looking at this graph, we notice here's our projectile. It goes up. Here's its maximum. It peaks right here, and then it starts going back down. So our maximum height, where would that be? So here's our maximum. If I look over at my axis over here, looks like these are by 5. So we have 25, 30, 35, 40, 45, 50. It looks right about 45. I would say the maximum height is around 45 approximately feet. Okay, How far does it travel before it hits the ground? So here's our horizontal distance, like they're markers uh, on a football field. How far does it go? Well, more than a football. This is in feet, so we're good. Okay, so 300 and just a more, this is 350 right here. Okay, and our limit here is 375. And these appear to go about by 10. So here's 300, 10, 20, 30, 40, 350. Okay, and so this would be 360, that next mark. It's between 350 and 360. We need to just go ahead and estimate. I'm going to say probably 355 feet. So our maximum height was 45 feet. Our distance traveled before it hit the ground was 355 feet. Okay, I'm going to go back to my paper now. Okay, so we now need to answer B, C, and D based on what we saw on the graph. The maximum height that the arrow reached we found to be 45 feet from our graph. How long was it in the air? We'll work on that in a second. How far did the arrow travel? How far did it go before it hit the ground? We found that to be about 355 feet. Okay, now how long was it in the air? Well, how far did it go before it hit the ground? Our horizontal distance, remember, is determined by this equation right here. Our x, or horizontal distance, is 120 cosine 25 degrees, or you can use 5 pi over 6 radians if you want, that's fine. Okay, and how far did it go? How far did it go before it hit the ground? We determined from the graph about 355 feet. So I just take my x here and I go, okay, well, when the distance x was 355 feet, how long would it take to get there, or what would t have to be? So we're just going to solve this equation for t. You put your distance traveled here and solve for t. So we calculate 120 times the cosine of 25. If you're using degrees, make sure your calculator's in degree mode. If you're using radians, make sure it's in radian mode. Okay, when you do that, you get about 108.76 t equals 355, and then just divide both sides by 108.76, and I will know how long my arrow was in the air. Okay, when I do that, I get that t is about 3.3. I get 3.26. I'm just going to round to the nearest tenth of a second. Okay, so it appears based on our graph that the time it was in the air was 3.3 seconds. Again, approximately, because we approximated the height and the distance based on our graph. So t might be a bit different than this if you have a trace function on your calculator, but it should be pretty close.